Alright, so what I'm going to do is I'm going to just play that video while I go up to my office to get more batteries, just because I'm not sure that this has enough battery power to last for the whole hour. Hopefully the volume will be loud enough so you can hear. Filled by more than 30 million people each year, all of them dreaming of returning home rich. Greetings, my name is Steve Miller. I'm a math professor here at Williams College, and I want to talk to you today about the implications of some of the math you've seen in high school and the billion-dollar gambling industry in Las Vegas. In particular, I want to show you some of the hidden connections between Fibonacci numbers and roulette. Roulette is a very popular game in Vegas. There are 18 red numbers, 18 black, and 2 green. You spin, and you bet $1, say on red. If it comes up red, you win $1. If not, you've lost $1. The game is so simple, many people believe they've cracked its secrets and can become rich. Let me tell you why they think so. So to simplify the analysis, let's imagine that there's no greens on the wheel. So half the time we get a red, half the time we get a black. So here's the strategy people like to use. Bet $1 on red. If it comes up red, we've won $1. If it comes up black, which happens half the time, we're down $1. So now, if we've lost $1, we now bet 2. So half the time red comes up, and we've now netted $1. We had lost $1 on the first one, we've just bet $2, so -1 plus 2 is 1. Half the time a black comes up though, and now we're down $3, because we lost $1 the first time, and we've now just lost 2. What do we do if a black comes up? We now bet $4 on red. So what happens? Half the time a red comes up, and we now net $1. Why? We lost $1 on the first spin, we lost $2 on the second spin, but then we gained $4 on the third spin. And -1 minus 2 plus 4 is 1. What happens if we got a black? Well, in this case, we're now down $7 because we lost $1, and then $2, and then $4. So we continue like this. Notice every single path ends with us netting $1. Each time we double our previous bet, and we eventually win $1. That's why this strategy is called double plus 1. You keep doubling your bet, and eventually you're plus 1. So lather, rinse, repeat. Every time we do this, we make $1. So why are we making this video? Why aren't we in Vegas playing this strategy and making money? Remember, Vegas is not in business to make you money. Someone has to pay for Mr. Smith's suits. We're missing something. What is it? So what are we missing here? Well, first, so what are we missing? So who can tell me what we're missing? Yes?
The 0 double 0.
Okay, so one is we're simplifying the game. You can actually put in the 0 and the double 0, make things a little bit harder. But why am I still teaching winter study? Why am I not in Vegas or Atlantic City, which is closer?
There's still a chance that you never win, and you just keep losing.
So there is the chance, but eventually, with probably getting as close to 1 as you want, I will eventually get the red.
I was in the double green.
Okay?
Casinos don't let you do this.
No, casinos would be thrilled for you to do this. In fact, what casinos now do is they will actually display the results of the previous spins on the wheel. So people go, oh, it's been red lately. Red is doing well. I should bet money on red. But there are other types of idiots. What are the other types of idiots? Yes. They don't care which kind of moron you are. You know, as long as you're the type of moron who has money and is willing to put the money down, they will take your money. They love people to do this. There's something you're missing. Any other thoughts?
So in roulette, does a bettor toss the ball, or does
it's
somebody
supposed
else?
to be somebody from the casino pushes a button or spins the wheel and it starts going, and there's supposed to be no way for them to have it stop on a certain color or number. And I will not say more because this is being recorded.
What happens if it lands not only on your color but on your number?
Then you just get you can make different kinds of bets. So this is a very simplified betting where we're only betting on color. But there is something wrong with the strategy. I don't love teaching this much. You know, if this worked, I would not be here. Okay. Alright, so there's actually 2 issues with this, although to keep playing. we may need to place enormously large bets. Imagine we have 20 blacks in a row. If that's the case, our next bet is over $1 million. We need more than just the willingness to make such a large bet, we actually need the money for the bet. As a mathematician, I don't mind assuming things to help me solve a problem. So let's assume we have an eccentric rich uncle. He's eccentric. He won't give us the money directly, but he will bankroll us at the table. Again, this is unrealistic, but if we can't even beat Vegas in this case, we have no chance in the real world. The second issue is that even though our rich uncle gives us the money to make the bet, he can't make Vegas take the bet. The casinos know math very well, and they place house limits on each table. They're like speed limits. There's a minimum and a maximum bet that we can make. The problem is we can very quickly reach the point where we need to place a huge bet, and even if we have the money to do so, we can't force the casino to take it. So it all comes down to the number of bets we can make before we exceed the house limit. And trust me, Vegas calculates this very carefully. Let's assume 5 consecutive blacks will bankrupt us. Let's let Pn be the probability we do not have 5 consecutive blacks in n spins, and Q of n the probability we do. Notice they have to sum to 1 because one of these two things happen. So let's find a formula for Pn. So we start, half the time we spin a red, half the time we spin a black. What's the probability we don't have 5 consecutive blacks in n tosses, given that the first one is red? Well, the red can't start a string of 5 blacks, so it's like we're spinning again, trying to avoid 5 consecutive blacks with n minus 1 spins. That probability, by definition, is Pn minus 1.
So this is the key observation here. If you want to have 5 consecutive blacks in n tosses, your first spin is a red, that can't start a string of 5 consecutive blacks. You can still have 5 consecutive blacks later, but you can't start off with 5 consecutive blacks. So really, it's now as if we're spinning n minus 1 times and not n times. And so this is how we're going to get our recurrence relation. So half the time we're going to be in this branch and have a Pn minus 1.
Over here, however, since we started with a black, that could contribute to 5 straight blacks, so we have to be a bit more careful. We spin again, half the time we get a red, half the time we get a black. Black, red can't start a string of 5 consecutive blacks. We have n minus 2 spins remaining. By definition, the probability we don't have 5 consecutive blacks is Pn minus 2. We continue like this, and after 5 spins, we have black, 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 red. That can't start 5 consecutive blacks. The probability of not getting 5 consecutive blacks in n minus 5 remaining spins is just Pn minus 5. But notice if we have black, 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 then we must have 5 consecutive blacks in our n spins, and so the probability of avoiding that is just 0. So we now get the following beautiful formula for P of n. P of n is half Pn minus 1, because half the time we land here, plus a half times a half Pn minus 2, because that's the probability we land here, and so on. So notice once we know 5 consecutive terms, we know the next, and we can just walk down the line.
So a couple of people had asked, well, what if they were greens? You know, what if there's a 0 and a double 0? So how would you change this if you had a 0 and a double 0?
It wouldn't be exactly a half.
It wouldn't exactly be a half.
Yeah.
So all you would do is, I think it's now 18/38. And so they would just change the numbers ever so slightly. But that's what's so great about this, is you can modify the algebra very easily.
So all we need is the first 5 values of P. Well, if we spin the wheel at most 4 times, we can't have 5 consecutive blacks. Therefore, P0, P1, P2, P3, and P4 are all 1. And then plugging this into the formula, we get P5 is 31 over 32, which is exactly what you would get if you directly analyze it. So marching down the line, we see if the wheel is spun 100 times, there's already over an 80% chance of going bankrupt. Math is filled with surprising connections. Your high school algebra is living the high life at the roulette tables in Vegas. So remember your math classes the next time you go there to gamble. Vegas did.
I will let the credits run since they are by Williams people. Okay? So this is one of my favorite applications of the Fibonacci numbers. One of my students at Brown was trying to convince his friend about this before he went to Vegas, sadly unsuccessfully. Okay? These calculations are done very quickly, very easily by Vegas. Now, most people are not going to be spinning the roulette wheel very can tell it was what it is. Most people at Vegas are not going to spin the wheel 100,000 times, right? So in terms of trying to calculate, very large numbers down the line, we don't actually have to worry about huge numbers like that. We talked about how would you actually evaluate the 200,000th term in the Fibonacci's, Benet's formula and all that stuff. If we're spinning things 100, 200 times, just march down the recurrence. And that's going to be more than enough for something like that. Okay, so what I thought I would do now is shift gears a little bit and talk about some basic combinatorics. And so, the very first project in the course that I hope some of you will do is the coding. If I give you a bunch of Lego bricks, how many different structures can you make? So how many people have never seen basically the binomial coefficients n choose k? Okay. So let me just briefly review what they are and then talk about one of my favorite problems. Okay. So binomial coefficients. So we start with, we have n people and we want to order them. So how many ways can you order n people? I like to think of having a bunch of boxes. And how many choices do you have for the first box? So I'm going to put the people who've never seen binomial coefficients on the spot and make you guys answer. So how many people can I put in the first box? How many options do I have for the first box? N. And now how many options do I have for the second box? N minus 1, perfect. And it goes all the way down to 1. So if you think of this almost like a tree structure, you have n choices in the first time. And then each one of these, you have n minus 1 choices here. And then each one of these would have n minus 2. And we don't want to keep writing n minus 1 all the way to 3 times 2 times 1. So we introduce a beautiful notation, the exclamation point. And so we call this the factorial. One of the things that's great in mathematics is you can define almost anything you want. Most of the things you want to define are not worth defining. Okay? What do you think? Well, let's do a few cases. Can someone tell me what 3 factorial equals? 2 factorial. 1 factorial.
1.
1.
0 factorial is 1 though.
0 factorial we define to be 1. So, again, we can define whatever we want. This turns out to be a really good definition. If you think about it, I give you 0 people. How many ways can I order the 0 people? There's one way to do nothing. Okay? What do you think negative 1 factorial would be?
1. Right.
How many ways are there to order negative a person? Can you order a negative a person? I might say negative factorial might be a negative number. I mean, a negative factorial might be 0. If you take advanced mathematics, you get some very strange things. Negative 1/2 factorial is the square root of pi. So it turns out you can actually come up with a function that generalizes the factorial function. It agrees with the factorial function at the integers, but at non-integer values it has some very new properties. So just for those who are interested, I'm just going to state what it is. It's the gamma function. And it's defined as gamma of s is the integral from 0 to infinity of x to the s e to the negative x to the s minus 1 dx. And as long as the real part of s is greater than 0, this makes sense. And it turns out, if you put in 1 more than your integer n, you get back n factorial, n greater than or equal to 0 in integer. Okay? We have people with a broad spectrum of backgrounds and interests in this class, so I want to just throw out a couple of things. I know at least some of you have seen this occur in various classes. So it's very strange that this function generalizes the normal factorial function. The standard proof of this is basically integrated by parts. So it's a really good exercise. If you integrate by parts, you get gamma of s plus 1 is s gamma of s. And that's integrate by parts. Okay. So this is a quick introduction to factorials. If I give you something like 4 factorial, 5 factorial, you can calculate that. What do you think 3 factorial would be? So the natural thing is to think, well, let's look at this as 3 factorial, which would be 6 factorial, which I think is 720. Yes?
Wouldn't it be 3 factorial times 2 factorial times 1 factorial?
That's another possibility. So let's come up with a list of all the different things we could have it mean. So 1 is 3 factorial is 3 factorial is 6 factorial is 720. Your thing on it was 3 factorial is 3 factorial, 2 factorial, 1 factorial, which would be 12. Any other thoughts?
3 times 1.
3 times 1. So 3 double factorial is 3 times 1. The double factorial actually means every other. So 6 double factorial is 6 factorial, is 6 times 4 times 2. And you stop at either 2 or 1. So again, you can define anything you want. It turns out this is a really good definition for combinatorial problems. What does that mean? It means when I'm actually trying to calculate how many ways can I do things, every other multiplication comes into play. I've never seen things where I have the factorial again, or the factorial with each term. There are situations where you can make that arise, but they do not really occur that frequently. I haven't really seen them. I have seen things like this. And so we'll get to something like that pretty quickly. Well, maybe I don't want to arrange all n people. Maybe I only want to arrange 3 people from the n. So if I only want to choose 3 people from n, and it matters, somebody's going to be the second in command, somebody's going to be a bad captain, somebody's going to be human resource. Okay? Different people have different positions. You will be distinguishable unlike the Lego bricks. Okay? How many ways can I take 3 people from n when order matters? So 3 from n, order matters. So what would that be?
I don't understand what you mean by 3.
So I want to choose 3 people from my n, and the order in which I choose them matters. The first person I choose will be president, second person will be vice president, third person will be secretary. So if I had to choose all n, it was n times n minus 1 times n minus 2, all the way down to times 3 times 2 times 1. But now I only want to choose 3 people. So what would it be if I only want to choose 3 people?
It would just be n, and then n minus 1, and then n minus 2.
Excellent. So the answer is n minus 1, n minus 2. So there's a couple of people who have taken math classes with me. Mathematically, what are my favorite things to do? Add 0, or if I can't add 0, multiply by 1. Much of mathematics is about doing nothing in a clever way. Okay? Really difficult proofs have you do nothing twice. Okay? This we only have to do nothing once. So n times n minus 1 times n minus 2. This begins to look like a factorial, but it doesn't go all the way down to 1. Well, we can fix that. Let's make it go all the way down to 1. n minus 3, n minus 4, 3 times 2 times 1. Am I allowed to just multiply by that expression? What do I have to do? Divide by it. n minus 3, n minus 2, 3 times 2 times 1. And so if I do this, what's nice is now I have a ratio of 2 factorials. And so now I get this is just n factorial divided by n minus 3 factorial. And this just becomes a convenient way of writing things. If you've defined the factorial function, this expression is n factorial of n minus 3 factorial. So how many of you have seen this expression before? How many of you would compute this quantity this way, as a ratio of 2 factorials? It depends on the system you're on. If you have a calculator, put in 100 factorial right now. Normally, between 60 and 100 factorial is enough to overflow your calculator. It depends, how good your calculator is. But the numbers just become so astronomically large, we'll say, okay, we've got a challenge. Can your calculator handle 100 factorial?
Yes.
All right, you have a good
That's a
calculator.
fancy
Does anybody else have a calculator or a cell phone? So take out a cell phone and see if your cell phone can do 100 factorial. You just can do it?
Yeah.
Impressive.
Good.
Can you do 200 factorial? No, okay, so
Yeah.
okay. So you can do
Yes.
200?
Yeah.
The answer is infinity.
Oh, this is oh, okay, should have. Oh, that's right. This only works for values that have been below or equal to 199. Once you hit,
Factorial.
you got 200 factorial.
With Wolfram Alpha.
I'm sorry.
Wolfram Alpha.
Oh, no, if you're using Wolfram Alpha, that's cheating. That's cheating.
So you have to,
You have to have your calculator in exam mode. Okay, so the calculators will overflow at some point. So if you're trying to do 200 factorial, there's a lot of extra calculations if you go all the way down and then you have all this cancellation, right? From a computational perspective, and this is not emphasized nearly enough in a lot of your math classes, which is why even if you've already seen this before, I don't mind taking some time today to emphasize this point. Theoretically, this is a wonderful formula. This allows us to understand many things about combinatorics. From a practical perspective, don't do this. Okay, you're doing far more calculations than you need. Gee, I could just multiply 3 numbers. Right? That's a lot better than doing this. Okay? In some books, they write this as NP3. N permute 3. How many ways can I choose 3 people from N when order matters? Okay? Well, maybe we want to consider related problems where order doesn't matter. So, can anybody give me a situation where I need to choose 3 people and order doesn't matter? 3 secretaries. 3 people in student government. Right, 3 councilors, 3 representatives. So I want N people, choose 3, order doesn't matter. So I'm doing a blitzkrieg review of this, I know this. How many ways can I do this where order matters? If order matters, what do I have?
N times n minus 1 times n minus 2.
N times n minus 1 times n minus 2. When you do problems like this on the board, you need names to give examples. You have 2 choices. You can have interesting names, fun names, and you can have boring names that are easy to keep track. Which do you prefer? Fun names? Alright. So if you want to do the boring names, it's A, B, C, D, E. Those are your people, and you want to choose 3 people from the set of 5. And if you want to do fun names, do Vader, Jar Jar. Hopefully we won't choose him. Leia, Luke.
You put Jar Jar second. Order doesn't matter.
Order doesn't matter. Yeah, thank you. What is his name? Grand Admiral
Grand Moff Tarkin.
Moff Tarkin?
Yeah.
Okay. Now, of course, we shouldn't have both Luke and Leia. Why? And for people, has everybody here seen Star Wars Episode 4? Alright, so for people who haven't seen Star Wars Episode 4, we have to be careful. I'll just say because they have the same initial. Alright? We'll leave it at that, and we'll put in Han. Okay? So, somebody give me a set of 3 people from our fun name list. This is not a hard problem.
Vader, Leia, Han.
I'm sorry?
Vader, Leia, and Han.
Vader, Leia, and Han. Thank you for not choosing Jar Jar. Okay? Give me another set of 3 people where order matters, where you're
Leia,
only
Vader,
using
Han.
Vader, Leia, and Han.
Leia, Vader, Han.
Okay, so now the question is, what's the best way to go through all the possibilities for these? I've got these three names. I think the easiest is to keep Veda fixed and start flipping here. So basically starting here with Veda. So Veda, then I can, after Veda, I can go Luke, Han, and, or I could go Han, Luke. And those are going to give me all the combinations starting off with Veda. So I could go Veda, Han, Leia. Now let's look at all the ones where Luke goes first. So I could go Luke, Veda, Han, Luke, Han, Veda. And then I have all the ones where Han comes first. So I could have Han, Luke, Veda, or I could have Han, Veda, Luke. I've gone through all the possibilities. How many possibilities are there?
6.
Try again. 3 factorial. Now, you might be saying, but isn't 3 factorial the same as 6? Yes. But I really want to view this 6 as 3 factorial. Once I have these 3 people, I have 3 factorial ways of permuting them. I have 3 factorial ways of assigning order. So if you look at the original problem, I wanted to choose 3 people from n when order doesn't matter. Well, I can do it when order matters, but what I've done is I've counted all of these orderings as different, and I don't want to count them as different. I want to consider Veda, Luke, Han the same as Han, Luke, Veda. Well, what's nice is you give me any set of 3 names. Doesn't matter what set of 3 names are. There's always 3 factorial ways to shuffle them around. So I'm always going to be able to divide by 3 factorial. I always overcount by the same. If I wanted to choose 4 people from n, how much would I be overcounting by? A factor of
4
factorial. So we get that our solution, so if order doesn't matter, it's n minus 1, n minus 2 over 3 factorial. And if you look at this, this is very similar to what we had a moment ago. This is screaming to be completed and go down to 1. Again, it's only screaming that from a theoretical point of view. From a computational point of view, leave it like this. This is a very easy thing to work with. But if we want to deal with the theory, I can multiply by n minus 3 factorial and divide by n minus 3 factorial. And now, what does the numerator become? N factorial. And notice this beautiful symmetry. N factorial over 3 factorial, n minus 3 factorial. So this is so important, we give it the name n choose 3. So we say n choose 3, and this is a binomial coefficient. There's lots of fun properties about the binomial coefficient. If people want, I can actually show you a movie that I'll be using in my Calc 3 class in the spring on fractal geometry, fractal sets, and binomial coefficients. There's really nice patterns that emerge and stuff like this. So I'm going to try to throw out some things. If you want to know more about them, email me and let me know, and I'll either do it in the class or I'll talk with you privately. But there's some really nice connections between binomial coefficients and fractal geometry. Is there anything special in this problem about 3? No. So if I wanted to do n choose k, what would be the only change? Just changes the 3's to the k's. How many of you have seen the 5th element? Do you think there's anything special about the number 5?
It's been a while.
Well, let me rephrase it this way. In the 5th element, do you think there's anything special about the number 5? Do you think they try to work the number 5 in to various places throughout the movie? More than they would try to work 4 or 18. So if you watch a movie like The 5th Element, you will find a huge number of occurrences of the number 5. If you look at how the time, if you look at the temperatures, they keep putting 5s in all over the place. Well, this is not surprising, right? The movie is called The 5th Element, right? For something like this, the logic we gave is the same if I do k or if I do 3. Alright, so what I want to do is I want to do a little bit with binomial coefficients now and then lead up to what I'll call the cookie problem. And this is a good way of looking at how to try to count how many different configurations can we have. So can somebody tell me in words, what does n choose k represent? Yes?
If you have a set n, then you need to choose k out of that n
Okay.
when order doesn't matter.
Good. So it's how many ways can I choose k people from n when order doesn't matter? So the first lemma is the following. N choose k is n choose n minus k. Okay? Can somebody tell me in words what this means?
Choosing k people out of n when order doesn't matter is they're the same number of combinations as choosing n minus k people out of n.
Okay, I would phrase it slightly differently, but you're correct with your phrasing. Your phrasing is correct.
So choosing k people for our committee out of n is the same as choosing which n minus k are not in our committee
Right.
out of n?
So here are our winners, and here, we'll be brutally honest, are our losers. Right? These are the people who lost, who don't make the committee. Right? I'm allowed to use phrasing like this, right? So choosing people to be in is the same as choosing people to exclude. If you've ever read, the Sneetches by Dr. Seuss, there are two types of Sneetches, those with stars on their bellies and those without. And they get all confused and whatnot. Hopefully you won't get confused in the combinatorics. But that's what we're basically doing. If you're in the group, that's the same as saying you're not in the excluded group. So really, that's the proof. Right? These have to be the same, because if I choose k people, then that's the same as looking at everybody who's left over and just calling them the losers. Okay? Normally in math books, they don't want you to phrase things like that. Okay? So they'll give you better names. You can prove this algebraically. N choose k is n factorial over k factorial n minus k factorial. This is the same as n factorial over n minus k factorial k factorial. Why is this true? Yeah, multiplication is commutative. I can multiply them in different orders. Now, if I have n choose n minus k, I want to have n factorial over n minus k factorial n minus k. So I now notice this is the same as n factorial n minus k factorial n minus k. So I've added 0. It's a good day for me. I've added 0, I've multiplied by 1, it's not even 11 o'clock. Okay? These are the same. And now, that's our definition of n choose n minus k. So this is an algebraic proof. In a math class, we put in a squared filled-in symbol like this. I was having a conversation with people recently as to, is this legal to use in the game of Pictionary? This is a way, some people write QED, it just lets you know the proof is done. Which proof do you prefer? Do you prefer the story proof, or do you prefer the algebraic?
Story.
I prefer the story. At the end of the day, I understand now why this result is true. When I look at it like this, I don't really have a sense of why this is true. I just did the algebra, and at the end of the day, everything worked. So what I want to do is I want to prove Pascal's triangle. How many of you have seen Pascal's triangle? How many of you know why Pascal's triangle works and the connection to binomials? Okay. So I'm at least hopefully choosing good math related to Legos that you haven't seen before and giving you good connections. And this is one of the things I want to do in the class. So lemma, n choose k plus n choose k plus 1 is n plus 1 choose k plus 1. And so the way you write Pascal's triangle the way you get each line is you add the two numbers immediately above it. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. And you have all ones going down. this line is what you get when you expand out x plus y squared. When you expand this out, you get x, oh, I did this one. You get 1x squared plus 2xy plus 1y squared. The coefficients here are just the coefficients in Pascal's triangle. And so there's lots of ways to prove this. This is the binomial theorem we talked about last time that we need. The general row, this row over here, would be x plus y to the fifth. And if you think about it, how this is going to be the term x to the fifth, x to the fourth y, x cubed y squared, x squared y cubed, x y to the fourth, x to the fifth. I'm sorry? Did I make a mistake?
Y to the fifth.
Oh, y to the fifth, thank you. It's fixed, okay. And if you think about it, what is x plus y to the fifth? It's x plus y, x plus y, maybe 5 is a special number, x plus y, x plus y, x plus y. This is at least the second time today 5 has appeared. How do I get a term? Well, I have to multiply this out. In each factor, I choose either an x or a y. Can I ever get a power greater than x to the fifth? Can I ever get a power greater than y to the fifth? And the sum of the powers of x and y have to be 5, because in each factor, I choose something. I either choose an x or a y. So the only possible terms I can have is x to the fifth, x to the fourth y, x cubed y squared, all the way down to y to the fifth. Those are the only possibilities. All that remains is to figure out what the coefficients are. So how would I get an x squared y cubed term?
Coefficient is 10.
The coefficient is 10, but how would I get that from here? I have to choose 2 out of the 5 factors to give me an x. So it's going to be 5 choose 2, x squared y cubed. Well, that's 5 factorial over 2 factorial, 3 factorial, x squared y cubed. And 5 factorial over 3 factorial, okay, that's 5 times 4 over 2, that's 10. And that's just 10 x squared y cubed. So these coefficients here are just the binomial coefficients. And this is the connection between Pascal's triangle and the binomial theorem. Okay, but now I generated this triangle by taking this and adding them. So somehow that must be a theorem. That the binomial coefficients satisfy this property. You take a number here, and it's the sum of the previous. So remember, if this is the third, if k plus 1 is 3, then I'm adding the second and the third from the line above. So if you've never seen this before, can somebody give me a way to try to prove this? How could we try to prove this relationship?
Algebra.
Yeah, roll up the sleeves, right? Or better yet, have one of your friends roll up their sleeves and have them wade through the algebra. If you do it, it will eventually work out. What's nice is you have an idea of what to prove. And you can cross-multiply, and at the end of the day, you'll get an equality. And if you want to be really fancy, you start with the equality and you work backwards, up until you get back to the original expression. Okay? So if you get really bored and want to do this, it's unlikely both will happen. By all means, feel free to try to do that throughout the rest of the class. Let me show you how to do this by telling a story. I need an awesome kick-ass school.
William.
Okay. I was gonna say, this isn't that hard, guys. And I need a school that sucks.
Yeah.
Alright. Alright. So we will prove this by considering Williams and Amherst. Because Williams is the great school, let's say we have n students from Williams. And we have one, it's being recorded so I won't. But their name starts with the right letter. One student from Amherst. Okay? I'm debating if I should send out the email that Amherst sent to their students warning them about their alums when they return to campus. Maybe I'll let you Google that. Google and just see what kind of school Amherst is. Anyways, we have n students from Williams, awesome kids, and we have one student from Amherst. How many students do I have total? n plus 1. And I want to form a group of how many people? What would you guess? I'm sorry?
K plus 1.
K plus 1. You had two choices. It's K plus 1. So how many ways can I form a group of K plus 1 people? So number of ways form a group of K plus 1 from N plus 1. Order doesn't matter.
Choose K.
I'm sorry?
N plus 1, choose K
N plus 1.
Choose K plus 1.
Choose K plus 1. Right? Now there are two possibilities when I form this group. There's of course many different possibilities, but there's two possibilities I really want to highlight and emphasize. What do you think those two possibilities are? So we're telling a story.
A group of only Williams students and a group of Williams and Amherst students.
Yes. Either unfortunately the Amherst student is hanging with us, or we're fortunate enough that the Amherst student is not contaminating our class. There's two possibilities. So here we have the Amherst student. Don't have Amherst. So we want to have K plus 1 people total. We have the student from Amherst. How many ways can I finish the group? So what would it be?
And choose K.
N choose K. I've got N students left from Williams, I have to choose K of them. If you want to be really fancy, you can write it as 1 choose 1. I choose the Amherst student. And now, of the remaining N people who are fortunately all from Williams, I take K of them. What about this possibility, the better possibility, when we don't have the Amherst student?
And you still have K plus 1 choices left.
So what would it be?
N over K plus 1.
And choose K plus 1.
Sorry.
So I've counted the same thing twice. Combinatorics is about counting the same thing twice. One way is typically easy, one way is typically hard. This was pretty easy. This is in some sense the definition of the coefficient. This was a little bit more involved, but if I add the two of them, it has to be the same. And so this is the story proof. So if you can tell stories, you can prove a lot of things in combinatorics. So if you like stuff like this, good classes to consider is discrete math. Another good class to consider is probability. These are classes that often use stuff like this to great advantage. Okay. Any questions on what we've done now? Yes?
Can you explain again why you chose a group of K plus 1?
I'm trying to prove this equality. And so by looking at Pascal's triangle, I had some inkling that a relationship like this holds. And so I want to look at N plus 1 choose K plus 1. And so when you're writing it like that, this plus 1 is almost implying that there's one special person. So there's lots of variants of this. Do people want to see another problem similar to this, or should I move to cookie? Typically, first person to speak loudly wins.
Cookie.
Cookies? Okay. For all of you who voted for morning and not afternoon, if it was afternoon, you could have had cookies for this. But it is too early in the day to take out cookies. Sorry?
We're in college.
Alright, I will then try to remember to bring cookies next time. So I call this the cookie problem. Other people call it the stars and bars, which is not nearly as much fun. How many of you have heard about the recent mega jackpot? Right. You can use this, what we're about to show, to analyze both that as well as a more complicated jackpot. How many of you are considering grad school? Alright. When I was a postdoc at Brown, there was a free food email list for the graduate students, where they would email each other and say, there's going to be a talk at 4 o'clock followed by this type of food. And the graduate, I could listen to that for pizza. Or, wait, all I'm getting is just some crackers. No, I'm not going to go to the talk for that. Just get you a sense of what grad school can be like. Alright? So imagine we have 5 distinct hungry grad students. The hungry is a little bit redundant. I will assume the graduate students are distinct and distinguishable. In mathematics this is true, in biology and chemistry, these lab sciences, it may not be true that professors can distinguish their students. I sadly know a graduate student who the professor had the wrong name for them, and they were too timid to correct the professor, who then started introducing them at conferences with the wrong name. We will assume that the students can be distinguished. I have 10 identical cookies. And I want to know how many ways can I divide the 10 identical cookies among the 5 graduate students. So all that really matters is how many cookies you get. Okay? Because we used fun names before, we'll use boring names this time. The graduate students named A, B, C, D, and E. I actually have been in schools where we don't refer to students by their names, but by the projects they're working on. Which is sometimes how when you have 2 people working on similar projects. We'll give them the boring names A, B, C, D, E. Can somebody give me one way to divide the cookies? Yes.
A gets 10, nobody else gets any.
Right. Everybody always starts off with giving A all 10. I think it's a great way to start. Right. Next. B gets 10. 0. And we go down for a while. It's not so bad. And then eventually, E gets all 10. Alright, now what happens? What do we look at next? So 9, 1, 0, 0, 0, 9, 0, 1, 0, 0. And then we can do all the different places to have the 1. And then we can do all the different places to have the 9. And now what comes next? 8 what? So then we do 8, 2. And after 8, 2, and we go through all that, then what happens? 8, 1, 1. Alright. You can see it's getting pretty bad. Right? I want to just analyze this a little bit, so you can get a sense of how bad this is, then you can get an appreciation of the power of stories. How many ways are there with the dividing by 10, where somebody gets 10 cookies? 5. Can somebody tell me why it's 5?
Because there are 5 distinct students.
Okay. And so
And
how?
only one of them can get all 10 cookies.
So it's, yeah, do it in binomials.
Sorry.
Or how many ways are there to choose one thing from 5?
See, you're now using the right words. How many ways are there to choose that lucky person to get all the cookies? And what will that be? 5, choose 1. Am I allowed to use corny jokes? Okay. Now let's look at 9, 1. How many ways are there to do 9, 1? 5, choose 2. What about 8, choose 2? How many ways are there?
5, choose 2.
5, choose 2. 8, 1, 1.
5, choose 3.
5 choose 3.
So I'm pausing here.
Oh.
The ones are the same.
The ones are the same. It matters who gets the 8 and it matters who gets the 1. If you don't think it matters, you will feel differently if you go to grad school. Getting 8 cookies is not the same as getting 1 cookie. It's not just 5, choose 3. What do we have to do? Order matters. So it matters who gets the 8. How do we fix that?
I have 5, choose 1 times 4, choose 2. Order doesn't matter.
Not quite. So 5, choose 3 is the number of ways of choosing 3 people to get cookies. And now that I have the 3 people,
There are 3 choices.
Three chooses.
There's 3 choices for who gets the 8. And if you multiply this all out, it turns out this is 5 factorial over 2 factorial, 1 factorial. So we get 5 factorial over 3 factorial, 2 factorial, 3 factorial over 2 factorial, 1 factorial, 2 factorial. The 3's cancel. So this is this way. 3 factorial over, yes. Okay, so it's 5 factorial over 2 factorial, 2 factorial, 1 factorial. What's really going on here is the way you need to look at this is of my 5 people, 2 people are the 1s, 2 people are the 0s, and 1 person is the 8. So what you're doing is you're looking at how many ways can I commute, but now certain elements are considered the same. So because these 2 are both 1s, when I was going through all my list, I have to worry about double counting. So Mississippi is a hard word to spell. It's a great word to use for this because you have 4 S's and all this stuff. Anybody know how to spell it? Very good. So you could play the games of how many ways can I rearrange the letters of Mississippi? How many distinct words can I do? Okay? The easiest thing when you want to do something like Mississippi, right? My spelling is atrocious, so if I've made a spelling mistake, please let me know. Alright, this is Mississippi. What I'm going to do is I'm going to attach labels. I1, I2, I3, I4, S1, S2, S3, S4, P1, P2. So how many ways, now all the letters are distinct, how many ways can I rearrange these 11 letters? Yes?
As long as the I's are in the 2nd, 5th, 8th, and 11th place, and the S's are in their same places.
I don't have to spell the word Mississippi. I could spell the word epicism. How many different words of 11 letters can I make from this? 11 factorial. But now, wait, of the 11 factorial, it doesn't matter which S is in a given spot. So if the S's are in spots 2, 4, 6, and 8, there are 4 factorial ways of rearranging the S's. Right? And so what would I have to divide this by? Because I want to now remove these labels. 4 factorial for the S's. Now what do I have to do for the I's?
4.
And for the P's? Anything else?
1 factorial for the
Yeah, we should really put in an M1 there so it doesn't feel left out. And put in a 1 factorial there. And the nice way of looking at this is now the bottom adds up to 11. It adds up to the top. So if you want to solve the cookie problem the way we were doing, have a lot of fun when you start to get to 6 cookies and all those different possibilities. You can do it. Okay? It's painful, but you can do it. Okay? I want to show you how to solve the cookie problem in 1 line. Okay? How many of you have seen Sesame Street? Right. This is probably the 2nd easiest question I can ask if you've seen Sesame Street. Which character from Sesame Street will be relevant for what happens next?
Cookie Monster.
The Cookie Monster.
No.
Alright.
Sad.
There's a great early clip where the Cookie Monster meets the Count, and the Cookie Monster wants to eat the cookies, and the Count wants to count the cookies. And Sesame Street wants to show people how to work out their differences. So in the end, the Count counts how many cookies Cookie Monster eats, and everybody's happy. I need the original classic Cookie Monster, not the politically correct bastardized version who says cookies are a sometimes food. I want the Cookie Monster who is always game to eat cookies. You ask him to eat cookies, he's there. The difficulty is having him only eat a specified number of cookies. Okay? So imagine the following. Add 4 cookies. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are 14 cookies. Okay? Classic original Cookie Monster comes and very happily eats 4 cookies, and then we pin him down. Alright? So let's say Cookie Monster eats these cookies. I claim Cookie Monster has just solved our problem. So what I'm going to do is I'm going to draw some lines. Let's count how many cookies are up to the first line. What do you get?
3.
Between the first and the second?
None.
Second and third?
3.
Third and fourth?
2. 2.
We have 5 numbers. What do those 5 numbers add up to?
10.
10. By eating 4 cookies, we basically put in 4 partitions. We've partitioned our set into a 5 tuple. How many cookies do you think A gets? 3. B, it's not their day. C gets 3. D, E. There's a 1-to-1 correspondence between the number of ways Cookie Monster can eat 4 out of 14 cookies and the number of ways we can go through and divide the 10 identical cookies among the 5 people. So all we have to do is figure out how many ways can Cookie Monster eat 4 cookies from 10. 14 choose 4. And that's the solution. Now, should we view this as 14 choose 4? I don't want to write it as 14 choose 4. How should I write the number 4?
10.
5 minus 1. This is really 10 plus 5 minus 1, choose 5 minus 1. That's a much better way to view what we're doing. Because that's the way that's going to immediately generalize. So now, the general problem, so the general case is going to be C plus P minus 1, choose P minus 1. Okay? So this allows us to avoid going through all those exhausting possibilities. And we can just jump to the answer. Does anybody have any issues with how we divided the cookies in the example I gave on the board, the 3, 0, 3, 2, 2? Is anybody bothered by that? I'm sorry? B might be bothered by this, okay? And so we have all these different constraints and requirements now, and it's considered inappropriate to have somebody not get any cookies. So what kind of constraints might you want to add to this problem?
Everybody gets cookies.
Everybody gets at least 1 cookie. So what I want to show you is I want to show you how you can recast what we're doing in terms of mathematics and just removing the word cookie. What we're really doing is we're solving the following problem. x1 plus x2 plus x3 plus x4 plus x5 equals 10. Each xi greater than or equal to 0 is an integer. We've just showed how to solve that. So we know the number of solutions, so this is just 10 plus 5 minus 1, choose 5 minus 1. Now imagine I want everybody to get a cookie. Well, maybe not everybody. Maybe the 5th person is from Amherst. Okay? And we're quite happy if the person from Amherst has no cookies. So maybe we want peoples 1 through 4 to get cookies. So we want 1, 2, 3, 4 to get at least 1 cookie. And what we can do is we can do the following. Let's let x1 be y1 plus 1. x2 be y2 plus 1. x4 equals y4 plus 1. And then x5 equals y5. So what I'm doing is I'm writing how many cookies do you have above and beyond the bare minimum that you're required to get. And so now if I look, my equation becomes y1 plus y2 plus y3 plus y4 plus y5 plus 4 equals 10. That's the same, it's the nice thing about being on the blackboard, is it equals 6. So I'm now solving the cookie problem with just fewer cookies. So how many solutions are there? So how many ways are there to divide 6 cookies among 5 people?
10 choose 4.
Okay, and I'm going to write the 10 as 6 plus 5 minus 1, choose 5 minus 1. So we'll do one more thing right now, and then we'll have like a 5-minute break, and then we'll do something on efficiency. Right now, we've divided up all the cookies. Every cookie is being used. Just like when we took the word Mississippi, we had to use every letter. What else might be the case?
Not use all of them.
Not. So can you consider why that might be useful for Legos? Why might we care about something like this? Yeah, you don't have to use all the bricks. If I give you 6 Lego bricks and ask you how many things can you build, it makes a difference whether or not you have to use all the bricks or not. So what if we now go back to the original problem, but not all the cookies have to be distributed? So we have 5 people up to 10 cookies are distributed. Remember, step 1 in the course is find a way to solve the problem. Don't worry about is it efficient. Can somebody give me a way to solve this problem? Yes.
How many ways are to distribute 10 cookies and then 9 cookies?
Excellent.
8 cookies?
So the solution would be the sum, C goes from 0 to 10, of C plus 5 minus 1, choose 5 minus 1. Okay? So this would be, how many ways can we distribute 0 cookies? There's only one way. How many ways can we distribute 1 cookie, 2 cookie, 3 cookie, all the way up to 10 cookies? Alright? It's not horrible, but there's 11 binomial, coefficients to calculate, and then you have to sum them together. I claim you can do this in 1 line. And I actually used this in a marketing paper I wrote a couple of years ago with a professor from Wharton. You can solve this in 1 line. You have to tell a story.
Has a 6th person to get rid of the extra cookies?
Yes. We call this person the professor. Okay? So you have an extra person, or a cookie monster, whatever. You have a sink. Any leftover cookies go to that extra person. Now, all the cookies are being used. So this is the same as 10 cookies to 6 people. And so what will the answer be?
10 plus 6 minus 1 to 6
10 plus 6 minus 1 to 6 minus 1. So more generally, if I have P people, this would be true. And of course, I don't have to have just 10 cookies. I'll be fancy C.
Don't you get rid of the minus 1s and the right one?
Oh, sorry. This should be P plus 1 minus 1. P plus 1 minus 1. Thank you. And we'll say now we have n cookies, and it would change like this. So we've just proven a major theorem. We've proven a theorem on binomial coefficients just by looking at how many ways there are to divide cookies. So again, this is the power of being able to tell a story. I know this is hard. This is a quick rush through the course. But now, hopefully, you're at the point, so the people who want to do Project 1, the coding, hopefully you've got enough of the basics of combinatorics and whatnot to start thinking about how many different ways can I combine things. Again, the difficulty is going to be when you have 2 structures that are equivalent. If you don't deal with that equivalence, the problem is much easier. How many ways are there to take the letters of Mississippi and rearrange them? If you consider the I's are all different, and the S's are all different, and the P's are all different, it's 11 factorial. That's really easy to work with. But from a practical point of view, can you tell the difference? No. And so you have to worry about, oh, I have to divide by 4 factorial, I have to divide by 4 factorial, I have to divide by 2 factorial. So that's the difficulty in project 1, is trying to figure out how to avoid double counting. Alright, so let's stop for about 5 minutes, take a break and stretch, and then we will resume